Yeah, my name is Shuolong Yang. I'm from the Pritzker School of Molecular Engineering from University of Chicago. So today, very glad to be here. Thanks very much for the organizing committee for giving me this opportunity to share with you some recent work from my group. In this audience, I find myself a little bit special because we're talking about very complicated quantum physics, but so far we have not really been discussing material qualities. So my group is actually the first group combining layer by layer material epitaxy with time-resolved photoemission spectroscopy. Some of you know me as a time-resolved ARPAS person, but today I'm going to wear a different hat. So I'm actually going to talk about material challenges and how we overcome material challenges to enable interesting quantum properties. So I call this the triumph and surprises when we push 3D quantum materials to 2D. And I'll tell you two stories. One is about a material triumph, and one is about a surprise. Does this work? Okay, let's all stay close to the computer. Okay. So I'd like to start with this interesting cartoon, which I stole from a website that's describing a very interesting concept called the dual vector foil. And this is a concept described in this famous three-body problem novel, science fiction novel. I'm curious, how many of you have heard about this dual vector foil? Oh, all right, excellent. Okay, many of you have heard. Great. So here's the concept, right? This is a weapon used by an advanced alien civilization that basically collapses our universe from 3D to 2D. So when I look at such rendered images, I cannot help wondering, oh, this actually looks interesting because you create edge state, right? So this reminds us of the picture when we, excuse me. This really reminds us of the situation when you collapse a 3D topological insulator into 2D. And in some favorable cases, you can have such topologically protected quantized edge state. That's what we want to create when we collapse our 3D, well, materials 3D world to 2D world. But there are notable challenges. This does not come for free. So the first challenge is material quality. So for this talk, I'm going to be focusing on material epitaxial growth. So this is a little different from mechanical exfoliation from 3D materials. So let me show you some pictures. So here I'm showing you two atomic force microscopy pictures taken on bismuth telluride, one of the iconic topological insulators, and some variations of bismuth telluride. On the left, for some of you who have experience with molecular beam epitaxy, so you can tell actually this is not a bad film, even though you show these triangular pyramids. Actually, the reason that you see these triangular pyramids is because it has very good crystallinity. So thermodynamically, it's actually much more favorable for the material, for the film to grow in this way. This is a good quality film, but it's not good enough. In order to really show the quantum effect, such as the quantum anomalous Hall effect, we need to go from good quality film to supreme quality film. That's what's shown on the right. So this one I just took from this famous paper by Professor Qikun Xue's group back when he was still at Tsinghua University. And this is on a chromium-doped bismuth antimony telluride. And you can see that there's a qualitative difference between these two. For the film on the right, you need really, really flat film that has uniform thickness across at least a micrometer range. So how do we go from the left to right? And if we can overcome this challenge, what kind of exciting physics that can we realize? So in fact, there was a missing opportunity from 15 years ago. 15 years ago, there was a very straightforward theoretical prediction when bismuth telluride was first proved to be a 3D topological insulator. And it's very easy to use, nowadays it's easy to use density functional theory to look at the materials when you push down to ultra-thin limits. So this is a table showing basically the gap at gamma and the parity of the gap when you push bismuth telluride down to a few quintuple layer thickness. And I'd like to particularly highlight this particular thickness, the 2 quintuple layers. So this is a thickness when the parity is negative and the gap is 148 millieV predicted by theory. So if this is true, this means that we have a topologically non-trivial gap that is many, many times of room temperature energy scale. So if this can be realized, we should have a high temperature or maybe even room temperature quantum spin Hall effect by now. So why have we not done that? So in fact, after this theoretical prediction, experimentalists were immediately motivated to look for such a phase. So again, this is from Professor Qi group. This still remains the best thickness-dependent RPES study on bismuth telluride films that I can find from the literature. So even after 15 years, this still remains as the best one. And even this one, you can see that it's not good enough. So I have RPES trained eyes, so I can look at the spectra and already I can see certain things that I want to see. But let's just be honest with the data. If you look at the 2 contemporary layer data versus the 3 contemporary layer data, so it's very difficult to see any difference, right? And most importantly, for the 2 contemporary layer critical thickness, it is impossible to really identify the inverted band gap. And this can be understood because, as we know, these materials tend to grow in this pyramid shape. So it's very difficult to obtain large area uniform thickness. I like to just fast forward to the data that I obtained from my own lab. So this is thickness-dependent data still on bismuth telluride. And here, we're very happy to see that there is a qualitative difference that we can see from this set of data. There is a digitized variation of the electronic spectrum layer by layer. So each layer corresponds to a completely different band structure. There are many interesting features you can find from such data, but I'd like to highlight a few interesting ones. The first thing is that if you focus on the valence band region, so the stuff that are lower energies, you can see that there is basically a layer by layer evolution of the number of subbands that you can see from such data. If you add one more quintuple layer, you find another pair of valence subbands. This directly comes from the particle in a box scenario along the z-axis. And if you look at the V-shaped feature, which we now know very well as the topological surface state, at 3 quintuple layer, the data is sort of interesting. So not only you get to see that linearly dispersing band, but close to that linearly dispersing band, there's almost like a shadow band slightly below the main band. And it even forms an anti-crossing with the valence band. In fact, what we're seeing here is the topological surface state from the bottom surface. Because we're getting to a thickness where the top surface and bottom surface start to hybridize with each other. And this is laser-based RPES, so this actually allows us to probe down to 3 quintuple layer below. And finally, for 2 quintuple layer thickness, which is the one that we hope to get, this is we actually clearly resolve this inverted band gap. It's about 100 millieV, so roughly agrees with the theoretical prediction. So you might wonder, what have we done differently to achieve the supreme quality bismuth telluride films? So I do not want to expand this into a material science lecture, but just want to mention one thing. Our film morphology is indeed quite different from what people traditionally thought about epitaxial growth of materials. In these films, so if you look at the transmission electron microscopy data on the right, you can see that when there is a step edge on the substrate surface, the material does not really want to break. So normally for epitaxial growth, just for everybody's information, there are step terraces on the substrate. And usually if your film is epitaxially strained, then it should actually have breakage near the step edge. But this one, instead of having a breakage, if you pay attention to the morphology of the film, it almost hovers above the substrate surface, forming almost like a almost freely floating morphology of these films. So it's a very special type of films that extends coherently without disruption by the substrate step edges. I call this the carpet mode of growth. As a matter of fact, because of this mode of growth, these films are exfoliable. So that's sort of amazing, just from an NBE practice. I'd like to quickly confirm that such materials are indeed topologically non-trivial. So we collaborated with Mark Hersam's group from Northwestern University and conducted scanning tunneling microscopy and spectroscopy measurements. Here, we just measure across the step edge between just the substrate surface, substrate is strontium titanate, and the 2 quintuple bismuth telluride. And then we plot the DIDV spectra for different spatial locations. And we'll observe that right at the edge between the topologically trivial STO surface and the non-trivial two-quintuplary bismuth telluride, there is an enhanced density of states right at the edge that if you take the representative curves from the middle panel, that's the curves on the right, you can actually see that the red curve, which represents the density of states obtained on the edge, fills that gap of 0.1 EV on the two-quintuplary spectrum. I should also quickly mention that we also did control experiments between the STO surface and one quintuple bismuth telluride, and indeed we did not see such topological edge states. So this may not come to us as a surprise. It has been theoretically predicted. It's really just highlights the possibilities when you can push the material quality to the next level. I'd like to also mention that because we can exfoliate such films, so it's actually become somewhat an interesting platform that we can just exfoliate and stack and twist and make interesting array structures. There have been lots of theoretical predictions saying that there are great opportunities to manipulate quantum geometry because these materials are intrinsically topologically non-trivial. So there's a bigger range of twisting angles such that you can manipulate the quantum geometry. Just want to highlight this interesting future opportunity. Okay, so this is the first story. Let me move on to the second one, which I thought could be a little more interesting. So there's another challenge when you push 3D materials down to 2D. And in fact, in many of these 2D quantum materials, there's an enhanced electronic correlation effect. Here, I borrowed data from my previous lab mate, now Professor Yu He at Yale University. And this is a series of RPET spectra taken at the antinodal point of the famous bismuth 2212 cuprate superconductors. So from left to right, you start from overly Hall-doped sample to optimally doped and then to underdoped sample. So for those of you who are familiar with cuprate high-TC materials, you realize from left to right, the electronic correlation is systematically increased. And what's really interesting from the electronic interaction point of view is that on the left-hand side, you can still define something called bands, right? You can define such a band structure, you can describe it using the language of bands. But on the right-hand side, you can barely use bands to describe what you see in such spectrum. And the reason for that is that that's a phase where people really have very poor understanding of what's exactly happening due to the many-body interactions. So this actually gives us not only some surprises, but also a great opportunity for us to exert actual control of quantum phases. So today, I would like to use this material platform to show to you that electronic correlation can be used as a very interesting knob to control topological quantum phases. So this material is a topological superconductor, and in particular, we're looking at the iron, tellurium, selenium. This is an iron cacao-chenide superconductor. It's an intrinsically a topological insulator, so it has its intrinsic topological surface state, but it's also a bulk iron-based superconductor. So I call this a self-proximity effect. So its own topological surface state couples to its own bulk superconductivity. So without much more engineering, it becomes a topological superconductor. But one thing that's being sort of ignored in the literature so far is that iron cacao-chenides turn out to be also one of the most strongly correlated iron-based superconductors. And here I'm really preaching to the choir because the study of strong correlation effect of iron cacao-chenides was spearheaded by Professor Ming Yi, who's sitting here, and also Qimiao Si, Professor Si, who's sitting here. And the question is, these iron cacao-chenides have some of the strongest strong correlation effect among all the iron-based superconductors, and whether such strong correlation do anything to the topological phase. So the interplay between these very important features, these two important features of such materials remains to be explored. However, there's a strong limitation on the bulk materials. For bulk iron, tellurium, selenium, as we look at the phase diagram, if you go from rich selenium to a selenium scarce phase, so once the superconducting dome is ended, you don't have a continuity of the phases. Actually, there is a antiferromagnetic phase near the iron tellurium side. So that is a problem because for this antiferromagnetic phase, it changes the symmetry of the material, it changes the Fermi surface topology. So in order to really clearly study how the strong correlation effect tunes the topological electronic structure, we need to do something to suppress the antiferromagnetic phase. So what we do is that we turn to molecular beam epitaxy. So we would like to grow such films on a substrate that has slightly different lattice parameter so that we can suppress the C4 to C2 phase transition. So to preserve the electronic structure even down to the iron tellurium limit. So that's the roadmap of the study. So let me show you our angle resolve photo emission study of iron, tellurium, and selenium. So the first thing we would like to do is to establish the topological superconducting state in our 10 unit cell thick iron, tellurium 0.93, selenium 0.07 film. So this is a thin film grown on strontium titanate that has slightly larger lattice constant than bulk iron chalcogenides. And for this material, so we use laser-based angle resolve photo emission spectroscopy. We can use the polarization control to highlight the different bands. So this is based on the so-called matrix element effect in photo emission studies. It turns out that for our measurement geometry, the S-polarized light highlights the topological surface state, which corresponds to a crossing feature. Now it's pretty common that everybody sees that now. And the P-polarized light actually gives us sensitivities to many of the other d electron bands, the dxy, dyz. The dxz is actually highlighted in the S polarization. So from such measurements, we do a systematic temperature dependence. We can compare the spectra for different temperatures, and we see that there is a superconducting gap opening on both the topological surface state, which is resolved by the S polarized light, and the bulk state, which is resolved by the P polarized light. And their superconducting gaps are differed by a notable amount, which is consistent with the proximity effect. So by this standard, we establish the topological superconducting state in such iron chalcogenide film. The most interesting part is what happens if we systematically tune the strong correlation effect. So this is done by just doing the stoichiometry change. So we just change the tellurium to selenium ratio. X here represents the tellurium content. X equal to 0 is iron selenide. X equal to 1 is iron telluride. So here we use the S polarized light to highlight the topological surface state. Going from left to right, we actually saw two topological transitions. The first one was sort of expected. So going from x equal to 0.6 to x equal to 0.79. So around x equal to 0.7, you can see that the electronic structure changes its shape. So there is a notable parabolic band for x equal to 0.6, but as you go to 0.79, it evolves into a crossing feature. And this crossing feature remains even up to x equal to 0.95, very close to iron telluride. But as you go from 0.95 to x equal to 1, there is something surprising happens. This was not predicted by previous density functional theories. So as a matter of fact, here, it looks like the topological surface state suddenly disappears. And instead, what we see is a shallow electron pocket near the Fermi level. I'd like to mention that such an electronic band structure is actually also very different from bulk iron telluride. So here I'm just comparing with the RPES data from previous studies on bulk iron telluride. The bulk iron telluride also shows a electron pocket, but the binding energy is completely different. If you look at the binding energy, that the bulk iron telluride has an electron pocket down to more than 150 MeV. But for our laser-based RPES on the thin film iron telluride, the electron pocket stays below 10 MeV. So it's very different in terms of electronic band structure. So what's happening here? So in fact, we can gain more understanding by looking at the bulk band structure as well. So here we just tune to the P-polarized light. And as you may remember, so the P-polarized light highlights the bulk dxy and dyz states. So the top is the RPES raw spectra, and the bottom is actually the second derivative, such that you can visualize the band hybridization much better. So there are a few things that we have observed that's happening to the bulk bands. First is that the dxy band actually becomes systematically flattened as you go from left to right. And that's kind of expected too, because so for such systems, the dxy orbital is the most correlated. As you go towards the iron telluride, it becomes increasingly more strongly correlated. The second observation is that the hybridization gap between the dxy and dyz band is systematically suppressed. So you can see that the separation between the top two bands becomes smaller and smaller, and down to iron telluride, it basically disappears. And lastly, the topological surface state still survives on most of the dopings, but up to iron telluride, we can barely call it a topological surface state. Actually, instead, what you see in the top right corner is what I call a vertical streak feature that is really, that you cannot really classify as a topological surface state. So, not all of them. Actually, X-1, so iron telluride has a resistivity downturn, but it doesn't completely go to zero resistivity. They all have a downturn, but X-1, I'm not sure if I can call it a superconductor. Yeah. One thing I should mention that's very important. So the AFM phase, antiferromagnetic phase, has a very strong signature, also a resistivity downturn, right? So you can measure, and we did not see that transition in these samples. So the strain really suppresses the AFM transition. This is 10 layers. So 10 layers, we chose the 10-layer thickness because this is thick enough such that you can talk about topological surface state, but it's also thin enough so that you can maintain the epitaxial strain.
You still have antiferromagnetic.
No, we suppress that order because it's strained by the lattice, by the substrate. Yeah, sure. So these behaviors are highly intriguing, and actually there is one underlying theme that allows us to understand all of these things, and it's actually related back to the orbital selective mod phase. So what's happening here is that the dxy band becomes increasingly more correlated, and the spectral weight starts to disappear near the Fermi level. And that can explain why it becomes flatter and flatter, and why the hybridization gap also is suppressed. But the last thing, it takes a little more effort. I'll explain to you in the next few slides. So for the topological phase in iron tellurium selenium, previously people have been using the picture on the left to understand what's happening. There is a band inversion between the chalcogen-driven PZ band and the DXZ band. That was the previous picture. Based on density functional theories, I would say it's largely a single particle-like picture. There's a recent theory done by Kotlier et al. Considering that there's actually a strong contribution of the dxy orbital into what's originally thought as the PZ orbital. In fact, they think that this should be technically called the xy minus band because it has a strong contribution from dxy, but it has odd parity. As a matter of fact, when the correlation in the xy minus band becomes so strong, it becomes flattened, and also it goes entirely below the xy plus band, the green band on the right. So this thing becomes topologically trivial again due to the strong correlation effect. So this is an insight that you would only get after considering the electronic correlations. And what this means is that the orbital character of different bands actually changes as you systematically increase the strong correlation effect. So what does it mean here? So in fact, as you systematically increase, yes, oh, sorry, 5 minutes. As you systematically increase the strong correlation effect in this PZ band, okay, so it should become strongly correlated, which corresponds to a band that is diffuse. And this is a self-energy effect, right? Because it becomes strongly correlated. So actually, we can compare our spectra. So this is our experimental spectrum taken using the p-polarized light to highlight all the features that we can see. And we compare with the calculation on the right. So this is a DFT plus dynamical mean field theory done by our collaborator, Professor Subhasish Mandel from West Virginia University. And this is done for the iron telluride in a strongly correlated limit. which really shows this streak feature in the middle. And I hope you can see the red color in that streak feature. The red color in there actually represents a strong contribution from the dxy orbitals. So this dxy component drives that band, that lower band, strongly correlated, which on this energy scale, it looks basically a vertical streak. That's due to the diverging self-energy effect. So this is how we can understand the strange, I'm sorry, that's a teaching reminder. This is how we can understand the strange electronic spectrum in the iron telluride strongly correlated limits. This is because there is additional band inversion due to the correlation effect. So I just want to show you that even though we don't have experimental data for this full calculation, but the calculation itself shows that if you can systematically tune the correlation effect, you can see how the originally crossing feature along the gamma z direction becomes increasingly going into a flat band regime where the reddish band lies underneath the green band, and that is the correlation-driven second topological transition. Okay, I think I'm going to end on this slide. So with that understanding, we really can redraw the phase diagram for the iron cacochenide topological superconductors. So the first topological transition around 0.7, that was predicted, that was expected, as you just change the tellurium to selenium ratio. But really, due to the strong correlation effect that the dxy contribution to the valence band makes this thing a correlation-driven topological trivial phase again. So this highlights the important role of strong correlation. You really have to tune the correlation to the right amount, not too small, not too big, to result in the right amount of correlation that leads to the right topological sorting phase. So with this understanding, let me land on this acknowledgement slide. So I'd like to thank all my collaborators and my own group members, and thank all the funding agencies for making this work possible. Thank you very much.
Question?
I have a question.
Yeah.
So for the first, actually, a question for the first and second part. So for the first part, with these ultra-thin bismuth selenide layers, is there any transport data on the putative helical edge states?
Not yet, not yet. So it turns out that these materials are still quite air sensitive. So in order to do transport, we need to figure out a way to actually protect the materials.
So then also with the iron superconductor,
yeah,
is there other direct evidence that the surface is actually topological, so vortex core states or edge states in domain walls or something?
So for thin films, I believe the answer is no. So I think for vortex cores, you would have to conduct a scanning tunneling microscopy to see the vortex cores. For bulk crystals, yes, there has been already data showing that.
This is Shuolong Yang's work, or
and his collaborators, correct? Yeah. Mm-hmm.
For this like experimental method, for example, do you expect wrinkles or breakage on flakes?
Yeah, so we can quickly go back to that slide. There are some. So that's actually just a picture under optical microscope. You can see that there are some wrinkles on that top membrane, but there's a significant region which is pretty pristine. Yeah.
And those regions are extremely flat.
Yeah. So as a matter of fact, you can do RPES on this. Yeah. Yeah.
Okay, I mean.
We have done some layer dependence. I think we have not grown thick enough to revive the AFM phase. So you're probably familiar that for bulk crystals around 70 Kelvin iron tellurides, you see a sharp resistivity drop. So we didn't see that for any of our thin film samples. So we took that as evidence that we didn't, the AFM was suppressed. We did lead low energy electron diffraction, and we saw some transition at 70K for bulk iron telluride, but not at for thin film iron telluride. Strain, yeah. So the bulk lattice parameter is about 3.82 angstrom. STO is 3.9. So roughly
tensile strain.
Right, so tensile strain, so.
But it's not uniaxial though, right? It's both, right? Both directions.
Right, it's biaxial, it's, right. Yeah.
Okay, last question, yeah.
Just a calibration, so.
Yeah.
Around 50-50.
Yeah.
Presumably you have a surface data which looks like the rat, maybe even two. And the question is, how do that part of spectrum compare with what has been observed on the surface of bulk materials?
They look pretty much similar, but there is a doping dependence. So if you look,
Just
Yeah.
around 50-50, or it has been most commonly studied.
so I have to actually make a clarification. The topological transition for the thin film sample happens around 0.7. It's actually not 50-50. There's a shift compared to the bulk. That's also due to the strain, because you actually change the effective tellurium angle.
But can you define sort of roughly the energy scale, say around not too close to 0.6, say 0.85?
Oh, you mean energy?
Just about 10, 20 MeV.
Yeah, you can.
Yeah, correct. Yeah, so that's about, I would say it's about 10 MeV. Correct. Yeah.
Okay, so let's thank him again.